Okay, right. Good evening. We'll start. Can you first confirm whether I'm clearly audible and visible? I can also check from my end. Can you confirm? Okay, right. Good evening. We'll start. Fine, right? Okay, it's working fine now. Okay, then we'll start. Right. Right. Okay. It seems still students are joining, but I will start because today the live stream is on YouTube as well. If you join late, you can watch that live. Right. Okay, we'll start. So today we are starting another milestone lesson, right? A milestone lesson that is electricity or current electricity. The reason to be this a milestone lesson is this contributes for 20% of marks, right? So we know mechanics is a 20% lesson we had actually. Mechanics is a 20% lesson we had. Then oscillations and waves is a 20% lesson we had. Then thermal physics was another 20% lesson we had. And now we are starting current electricity, the last 20% lesson we have. The last one, right? The last two lessons we covered in the reverse class were both 10% lessons, matter and radiation and properties of matter. They were 10% lessons. And today we are starting current electricity, a 20% lesson, and the last 20% lesson you are going to learn in our syllabus, right? The last 20% lesson. And most importantly, other than that contribution of 20%, there are links, major links. There are major links with the following lesson, electronics, and also with magnetic fields, right? So therefore, if you didn't have a solid understanding about electricity, you will find it difficult to do electronics and magnetic fields as well, right? So therefore, this is kind of a critical and a crucial lesson in terms of the number of marks you get, in terms of the gravity, the allocation of marks you can score, and the other thing is with the links of the following lessons, right? Two things. Links with ready, lagunut ready, right? And to be honest, this is a very easy lesson, right? If you are in the class from the beginning and if you understand everything from the beginning, from zero, from sketch, right? I will explain everything starting from the simple things, right? No need to worry, we will explain everything. You will get to know everything starting from scratch, right? So by the end of the class, by the end of today's class, will be covering all the fundamentals we have here in current electricity, right? Fundamental things, and the things we are covering today, we are going to cover today, the fundamental things, right, is the foundation for this lesson, right? So you will see the foundation of the lesson today, the foundation. Once the foundation is firm, easily we can build up walls on the foundation, right? So stay focused and stay vigilant in the class, because now there's a kind of a rumors වගේ එකක් among students that current electricity is kind of difficult. No, current electricity is one of the easy lessons we have, right? I can't say easiest, but comparatively an easier lesson we have, as long as you have a solid foundation. Don't worry, and you can secure these marks. 20% of marks is there in the paper, and the good thing is we are just 18 weeks from the exam, right? You are just 18 weeks from the exam now, right? It is exactly 18 weeks and 1 day now. Exactly 18 weeks and 1 day. Just 18 weeks. A very small time. right? Just 18 weeks. And here we have current electricity. These are the lessons to be covered in our class. Current electricity, right? I mean, for 26 batch, electricity, then electronics, and electric fields, magnetic fields. Now still you got this is on Thursday. And for Lisa that is on Monday, Thursday or Monday, and these two will be on Saturday, reverse class on Saturday, and allocation here is 20%. See, still you have some life-changing amount of marks available, right? Still 20 marks here, 20% here, and 10% here, 10% for all fields, right? 10% here, right? Tamat 40% එකක් තියෙනවා. Still you got 40%. Still you got 40%. Right? Still you got 40%. And for structured essays also we have 80 marks, no? Right? 80 marks කියලා කියන්නේ out of 50, that is 20 marks, right? That is 20 marks, right? So they are like life-changing marks. They are still available, right? So even if you are not that familiar with, say, some of the lessons in between, but yet we have 40 marks remaining just for these lessons. We are yet to cover, right? 40 marks. 40 කියලා කියන්නේ ලොකු ගානක්. It's 40, right? And 3 more practical seminars also coming up, right? 3 more practical seminars also coming up. So ඒ වගේ ගන්න පුළුවන් marks ගොඩක් තියෙනවා. Practical seminars වල we have conducted 2 already for mechanics and waves, and sooner we'll be having the optics one, and optics, thermal and current electricity seminars are coming up, right? So there are more marks to be collected, right? So even now we have more marks to be collected. The only thing is have a good focus, right? Have a good focus, have a dedication. You have 18 weeks and utilize these 18 weeks without wasting time, right? So this is a time battle. It is a time battle. All about managing time. All right then. Then other than covering theories, now I'm now including all the questions up to matter and radiation in my papers. In last week paper also you got an essay from matter and radiation, and you got an essay from properties of matter, right? So likewise you are getting essays from all the lessons we have covered now, and sooner, next month or in another 1.5 months of time, we will be starting full syllabus papers, right? So more things are coming up, and new year is also coming up. So even you have the new year, don't lose the momentum, right? New year is only on 14th, right? So on 14th you can celebrate new year, and you have to come back to the track again as soon as possible. Even a day counts, right? Even a day counts now, right? It counts now. Even a day counts these days, right? So in terms of days, you got around 100 to 110 days now, right? That is only 18 weeks. Right? So then let's get into the thing. Put down the heading as current electricity. Current electricity. Right? Current electricity. First, let me explain the gravity, right? How this 20% is broken down. Always when you learn a lesson, right? Always know the gravity of the lesson. Gravity in the sense, know the allocation of marks about the lesson. Then you know where to score, right? Where to score and how you can score with a particular lesson. That idea is a must-have idea, right? current electricity. When comes to MCQs, you are getting 6 to 7 MCQs. 6 to 7, right? 6 to 7 MCQs means, right, about 7 final marks here. About 7 final marks here. And structured essays, you have one structured essay, right? You have one structured essay. That is actually structured number 4, right? Number 4, not 4 structured essays. Structured number 4. Structured number 4, right? Usually number 4. Usually number 4, right? One structured, that is number 4. One structured number 4, and it has 20 marks. 20 marks. Then from 100, that is 5 marks. 5 marks out of 100. In essays, essays, a definite essay, right? This is also a definite one. This is also a definite essay. One definite essay, right? That is 9A as the question number. 9A. 9A. One definite essay. It carries 30 marks. It carries 30 marks. Then 7.5 out of 100. 7.5 out of 100. So altogether, this is 7 plus 5, 12, 7.5, 19.5. So we say this a 20% lesson, right? We see this, but 20% lesson. The last 20% lesson you are learning, right? The last 20% lesson, but with the contribution to electronics is fully depending on current electricity. Electronics is also a lesson which carries 10%, no? Right? 10% in electronics is decided by electricity. 10% in electronics is decided by electricity, right? So that's why we are learning current electricity before electronics, right? That's how it should be. That's how it should be. And for magnetic fields also, we have an relation from fields, no? Then even though it's 20% alone from current electricity, but with the links and everything, it has more than 30, around 35% of marks is linked to current electricity, right? More than, like, around 35, more than 30. It's around 35% of marks is linked to current electricity, right? That's a huge amount. That's a huge amount, right? Okay. So you all know 2025 results are also released, no? So as a batch, they have good results, and they had some postponements and everything, but yet most of them have managed to, like, done the exam in kind of a anticipated and the good manner, right? So they all have got good passes, good grades, right? And in your case, you are going to sit for the exam just in 18 weeks, and you are going to receive your grades results by the by December, right? So time flies, right? Time flies so fast. By December, you will also get your results, right? The first call I got this time was the best call, actually. It was the district 38th one, a bio student, right? It was the first call I got around 11:45 or something. It was released around 11:30. 11:35, 40, I got the first call, right? 3 years with the rank 38, right? So likewise, in December, I'll be getting calls from you as well, right? So time flies so fast. You are sitting for the exam in 18 weeks, and just after 3 months after the exam, you will get your results, right? So work hard, right? So this is the allocation. This is how marks are allocated, right? So let's start. Right. Okay. So first, let's see what electric current is. As a first subheading, write down electric current. Electric current. Write down electric current. Electric current. electric current. Electric current. Right. Listen, look at the word. Electric current is defined as this. I equals Q over T. Electric current is defined as I equals Q over T. This is general equation. I equals Q over T, where I is electric current. Where I is electric current. Q is amount of charge. Amount of charge. T is time. Right? T is time. Take down the equation and introduce term. Introduce terms. I equals Q over T. I equals Q over T. I equals Q over T. And the other thing about current electricity is some basics like Ohm's law, V equals IR, basics like Ohm's law and V equals IR, you have come across, at least you have come across in O levels. So we'll be connecting those things you know with the things we learned today, right? And you can like gradually build up your foundation and make it solid, right? So stay vigilant from the start and stay focused, right? And by the end of current electricity, you have 20%. 20% it's a definite one. No? Unlike other lessons, a definite 20% is there, right? I electric current. Introduce terms. I electric current. I electric current. I electric current. Once on YouTube, right? You can forward your questions if anything through the live chat, right? I electric current. Q amount of charge. 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 And T time. T time. T time. I electric current. Electric current. Q amount of charge. Amount of charge. T is time. Right. Listen. So we know when it comes to definitions, anything over time is defined as a rate. Anything over time is defined as a rate. 1 second. All right. Anything over time is defined as a rate. Defined as a rate. So this should be rate of charge flow. Q over T. No? So that's a rate. Q is amount of charge. So this is the rate of charge. So that is defined as rate of charge flow. Write down below with a red pen. This is a definition. Write down below with a red pen. Write down below with a red pen. Write down below with a red pen. Rate of charge flow. 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 Rate of charge flow is defined as rate of charge flow is defined as rate of charge flow is defined as electric current. Rate of charge flow is defined as electric current. Rate of charge flow is defined as electric current. Rate of charge flow is defined as electric current. Right. Listen. So we all know that as the current or as the charge, right? We know electrons are flowing, no? Right? That is electrons. That is electrons. Electrons are flowing as the charge. Then this charge is given by or charge is generated here by or the contribution with electrons, no? Right? Which means we are going to convert this to electrons using charge of an electron. Right? Write down below. Normal color. Use a normal color. Since electrons are flown, use normal color. Since electrons are flown. Since electrons are flown, since electrons are flown to cause electric current, to cause electric current, since electrons are flown to cause electric current. Listen, we know then total charge or amount of charge can be written as n times E, number of electrons into charge of an electron, number of electrons into charge of an electron, right? Then using the general equation, right? Using the general equation, we know I equals Q over T, but now Q can be written as Ne, right? So it can also be written as Ne over T, can also be written as Ne over T, right? Where N is number of electrons, E is charge of an electron. Take it down. Take it down. Take it down. Right? I equals Q over T, Q equals Ne, so that is Ne over T. Introduce terms. Introduce terms के लिए अभी मेरे terms का मतलब introduce कराने. So we'll introduce only N and E. N number of electrons. Number of electrons. N number of electrons. Number of electrons. Number of electrons. E charge of an electron. E charge of an electron. E charge of an electron. In Matan edition also, we discussed about this. I mean, you know this. We have come across about charge of an electron. Charge of an electron within brackets, you can mention the value 1.6 times 10 to the power minus 19 coulombs. 1.6 times 10 to the power minus 19 coulombs. 1.6 10 to the power minus 19 coulombs. 1.6 10 to the power minus 19 coulombs. Right. Listen. Listen. A small task. Find units of I using these equations. Find units of I using these equations. You won't be asked about dimensions of I because we only have MLT as dimensions for A levels, right? We don't have the dimension of current electricity, sorry, electric current, right? We don't have the dimension of electric current. But MLT, even though there are 7 different dimensions for 7 fundamental quantities, we have only 3. Therefore, dimensions won't be asked, but units will be asked. Find the derived unit using the equation. Quickly. That's it. Okay, all right, we have answers. CS minus 1, right? CS minus 1, coulombs per second, right? Coulombs per second, CS minus 1, coulombs per second, because units of I is given by units of Q over units of T, right? Charge is measured in coulombs. Time is measured in seconds. So that is coulombs per second, CS minus 1. CS minus 1. But we all know from our unit 1, SI unit of electric current is not coulombs per second, but amperes. That is amperes, right? Which means this is a derived unit. But the SI is amperes, no? Amperes means CS minus 1, right? Don't write this, right? But the SI unit is amperes, which means amperes means CS minus 1. Right? So if we need to expand amperes using the derived unit, right? Amperes means coulombs per second, right? SI is amperes, like Newtons kila kiyane kgm is minus 2. So likewise, amperes kila kiyane CS minus 1, right? So after this, write down in red, but SI unit of electric current is, after CS minus 1, write down in red, but SI unit of electric current is, SI unit of electric current is amperes. But SI unit of electric current is amperes. Therefore, amperes equals CS minus 1. Therefore, amperes equals CS minus 1. Amperes equals CS minus 1. Amperes equals CS minus 1. Right. Okay. Let's move on. Next heading. Write down variations of resistance and resistivity. Variations of resistance and resistivity. Variations of resistance and resistivity with temperature. Variations of resistance and resistivity with temperature. Fine. Listen now. Listen. Don't worry about the terms resistance and resistivity for a moment, because all definitions are coming up. Before moving on to those definitions, first we have to know these variations, right? Then hold on for a moment until we finish the variations. Then we will be stepping into resistance, resistivity, and you will see what actually means by resistance and resistivity there, right? Even though you don't know about resistivity, right? I'm pretty sure that you have heard at least resistance. So basically, for a moment, keep in mind that resistance is the disturbance to carry current that is in a substance, that is in a material, right? In any material, there's kind of a disturbance, right? Disturbance to flow current, flow electrons. That is called resistance, basically, right? Okay, now what we are going to do here is this. In current electricity, listen, in current electricity, we are categorizing substances we have under 4 categories. We are categorizing substances we have under 4 categories, 4 different categories, right? Namely, conductors, right? Conductors means electric conductors, insulators, semiconductors, and superconductors. Categories hadaraktheno. So we are going to check their variations of resistance and resistivity with the reasons in this part, right? So we will go as conductors, semiconductors, insulators, and superconductors, right? As number one, write down conductors. Look at the board. So I'm plotting R is the symbol for resistance and rho is the symbol of resistivity, right? R is for resistance. These are standard symbols. R is for resistance. Rho is for resistivity, right? Now, if we plot this variation, listen, if we plot this variation, experimental results, this is what you get, right? I'll explain this again with an equation also. Equation app, right? So basically, to plot this curve, we can easily do this with an experiment, right? This is the curve we are getting, right? Both R and rho increases, non-linear, right? Main purpose here is we are going to check the reasons. We are going to dig deep into the reasons for this behavior, right? Reasons for this behavior. Listen, don't write down, just listen. The reason to put this arrow is, fine, I think you have seen arrows in, you have seen arrows in some graphs in thermodynamics. You have seen arrows in viscosity graphs. You have seen arrows sometimes in elasticity graphs, stress strain curves. So arrows in graphs. The reason is we are plotting the graph with increasing temperature. We are plotting the graph with increasing temperature theta. We are plotting the graph with increasing temperature. Right? That's why the arrow is put, because there are some substances, they behave in different manners when increasing and decreasing temperatures. Right? So this is when increasing. Listen, this is the reason. We know if there is a conductor, listen carefully, very important. If a substance is a conductor, naturally, almost all atoms in that conductor are ionized. Ionized means they have polarities. They have plus minus, right? They have polarities. Ionization. They are ionized, right? Plus minus plus means they have basically positive protons and negative electrons in the material, in the substance. When temperature increases, what happens is vibrations of electrons increases. When vibrations increases, the smooth flow of, or the streamlined flow of electrons is harmed, because flowing a current means flowing electrons. Then that smooth flow of electrons is harmed with the vibrations. The electrons vibrate when electrons are vibrated, that smooth flow of electrons is harmed. When smooth flow of electrons is harmed, right, current decreases, because current is the flow of electrons. Then current decreases. When current decreases, resistance is the disturbance for current. Always IN are inverse, right? Then when current decreases, resistance and resistivity increases, right? So basically what happens is, don't write, look at the board, right? Basically what happens is, when temperature increases, because the collisions between electrons increases, the streamlined flow, smooth flow of electrons is harmed, right? That is harmed. Because of that, current decreases. When current decreases, both R and rho increases. Both R and rho behaves the same, and always resistance and current are inverse. Always resistance and current are inverse. So basically, this is what is happening. So likewise, under each type, like conductors, semiconductors, insulators, superconductors, you will be seeing the reasons for these behaviors, right? Okay, now take down only the graph. Take down only the graph. Copy down only the graph. Only the graph. So I hope all of you are aware that set of people, a group of people of 4 is are on the way to the moon, right? So lots of things are happening nowadays, right? It's kind of happening, and I saw they have declared that they are halfway through around now it's 7:40. I saw it around 1:30 somewhere around, right? So by the afternoon today they were halfway through the journey. They were halfway through the journey. They are traveling for 400,000 kilometers from Earth to moon, right? Very interesting. And have some idea because most probably you will get a question from this thing, moon landing, in your common test, right? In your common general test this time for sure you will get a question from that, right? What's the name of the shuttle? Shuttle එක නම මොකද්ද? General knowledge. දන්නේ නැද්ද? Orion is only the capsule. අර උඩ තියෙන part එක විතරයි ඒක. What's the term for the entire shuttle? Rocket and the capsule both. Orion කියන එක හරි, that's only the capsule. That's only the capsule where the people are. Shuttle කියලා කියන්නේ the entire thing. So it's 400 kilometers away, and now they are traveling in a speed more than 300,000 miles per hour. Miles per hour at the moment. At the moment, they are traveling more than 300,000 miles per hour. Right? They launched this around 200 miles per hour, and after the aerosphere, they have increased their speeds to like these levels. It's more than this now. It's more than this, and they are like halfway through. Not now actually. They were halfway through by the afternoon today. Right? So let's see, because things are happening and people are going to step onto moon after 63 years. After 63 years, right? Quite a huge time period in between, and we don't know whether they actually went there for the first time. There are lots of contradictions going on about the first moon landing using Apollo 11 and Neil Armstrong and the group, right? There are lots of contradictions going around, lots of things going around. Now we don't know whether it's 100% accurate or were they actually step into the moon. We don't know, right? Because by 1963 there were not that like improved technologies, I mean like evidences. Because of that, then there are some constraints for finding them, right? So දේවල් කියනවා. Some are saying that they were building a model in Area 51 in US, and some photographs are captured and released to the internet, something like that. Right? Now this time they are actually in the shuttle, and they are on the way now and halfway through. If you are using Facebook or something like that, you better follow NASA page these days, right? So they are posting updates regularly, and there were some voice clips also. They are saying that it's too cold and those things. I heard some voice clips, right? So very interesting, very interesting. So in a free time, you just get some updates about these things, and for sure it will come in your common general test this time for sure. Right? Why the curve is starting a little lower? Because even if the resistance is, if the temperature is 0, resistance is not 0 of a material. So is the y-axis of graph r rho, or can that curve be drawn separately for r and rho? Both behaves the same. Then both are here. Both are here. Both behaves the same. Both behaves the same. Right? එකම curve එකේ ඉන්නේ දෙකටම. Artemis මං private නේ දාලා තියෙන්නේ මං දැක්කේ නෑ. Artemis, yes. මේ තියෙන්නේ divided by නෙමෙයි r o rho. R rho rho. Both behave the same. R o rho. R rho rho. Artemis තමයි shuttle එක. And the Orion means the capsule. Capsule එක විතරයි දැන් යන්නේ because the rocket has already came back. Right? එයා aerosphere එකෙන් එහාට දාලා එයා එනවා. Gravitational fields. Right? Okay, that's enough. Write down below in point form. First point. Almost all atoms are ionized. Almost all atoms are ionized. Almost all atoms are ionized. In natural state, almost all atoms are ionized. In natural state, of a conductor, in natural state of a conductor, right? Right in point form. Second point. When temperature is increased, collisions among atoms, collisions slash vibrations among atoms, increases. Within brackets again, collisions among electrons, right? Atoms කියලා ඉන්නේ මොනවද? Protons and electrons, no? So electrons are also there. Within brackets, collisions among electrons. Third point. It impacts on smooth flow of electrons. It impacts on smooth flow of electrons, and it reduced electric current. Right? Then write this using red. Therefore, when temperature increases, current decreases, R and rho increases. Write this in red. This line. Write this line in red. Write this line in red. Okay, right. Next heading, semiconductors. Next heading, semiconductors. Number two, semiconductors. Semiconductors. Okay, chemistry people. Chemistry people, what is a semiconductor? What is a semiconductor? One more thing. Oh, wait. One more thing we have to mention here. One more thing. There's a variation for this. There's a variation. Variation means equation, right? We'll mention the equation as well. So below this, mention the equation 2. Equation is r theta equals r naught 1 plus alpha theta for a conductor, right? Mention this. R theta equals r naught 1 plus alpha theta, right? It should come under conductors. This mention r theta equals r naught 1 plus alpha theta, right? You know this shape of the graph, shape of the equation actually, because of thermal expansions, same shape, right? Introduce terms, right? Make a conductors r theta, r naught, alpha, and theta. Introduce terms, r theta, resistance at theta degrees Celsius. Introduce terms, resistance at theta degrees Celsius. This should come under conductors. Make it pass. After this line, mention the equation and introduce terms. R theta, resistance at theta degrees Celsius. Right? Make a important theta degrees Celsius. Kelvin's back, right? Theta degrees Celsius. R naught, resistance at 0 degrees Celsius. R naught, resistance at 0 degrees Celsius. R naught, resistance at 0 degrees Celsius. Alpha, temperature coefficient of resistivity. Temperature coefficient of resistivity. Temperature coefficient of resistivity. Right? And this is also called resistivity coefficient of temperature. Right? Resistivity coefficient of temperature more common name is temperature coefficient of resistivity. Right? Sometimes it's also known as resistivity coefficient of temperature. Right? Alpha and theta egat Venus present temperature, not the temperature difference, present temperature, because one end of here is at 0, no? That's why one end is at 0. Compare this with thermal equations. Same shape of the equation. Right? Present temperature. This is temperature coefficient of resistivity. Right. So R theta equals R naught 1 plus alpha theta. Now let's move on. Semiconductors. Put the heading now. Second one. Semiconductors. Look at the board. Theta. Rho. Right. Here, what happens is R and rho decreases like this. R and rho decreases. Right. So let's check the regions. And I ask you a question. Right. What are semiconductors? Chemistry people. Now I told you what a conductor is. Connect this with like chemistry, I think in O levels also about conductors, semiconductors. I guess it's in chemistry. A levels කොහොමද තියෙනවා? An element acts as a metal and an unmetal. In between, actually, in between, I'm asking semiconductor in terms of ionization. What can you say about ionization of a semiconductor? I'm just checking your chemistry knowledge. 18 weeks. What about the ionization of a semiconductor? The conductors among you, they are fully ionized. Right? All atoms are completely ionized. What about semiconductors? About ionization? Another. Yeah, they are actually partially ionized. They are partially ionized. Right? They are partially ionized. Guess on the they are partially ionized. They are partially ionized. Right. Semiconductor එකක් කියලා define කරන partially ionized එකක්. Right. Now this what is happening. Listen, listen. Now natural state, in the natural state, atoms of semiconductors are partially ionized. Partially ionized. When temperature increases, non-ionized atoms are also becoming ionized. When temperature increases, non-ionized atoms are also becoming ionized. Then number of ionized atoms in the material increases. No, when number of ionized materials in the ionized atoms in the material increases, which means ionized electrons, free electrons increases. Free electrons increases. When free electrons increases, it supports, it contributes more current flow. Right. So what happens is when theta increases, right, since non-ionized atoms are also ionized in a semiconductor, current increases. Free electrons, flow of free electrons increases, so I increases. When I increases, we know I and R are always opposite. No, both R and rho decreases. That's what happens here. That's what happens here. You should be able to explain them, right? In essay questions, usually these explanations are asked, right? You should be able to explain them. Okay, take down the diagram. Only the graph. Diagram. Graph. Take down the graph. Only the graph. Take down the graph. Only the graph. Make only the graph. Only the graph. So, but if more atoms are ionized, wouldn't there be more electron collisions? Listen, that's a good question. Listen, no, because using the heat, atoms are becoming ionized first, using the heat, right? Now, if they were already ionized, then the additional heat, excess heat that is coming into the material is used for collisions. But now, before starting collisions, there are non-ionized particles, no, non-ionized atoms, so they become ionized. Right? Then there won't be any redundant energy, excess energy remains in the system because they are used to ionization. Right. Right down below in point form, first point, atoms of semiconductors, first point, atoms of semiconductors are partially ionized. Atoms of semiconductors are partially ionized are partially ionized in natural state 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 are partially ionized in natural state. Second point, when temperature increases when temperature increases non-ionized particles are when temperature increases non-ionized particles are becoming ionized. 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 Next point. Therefore, current flow will be higher. Therefore, current flow will be higher. Therefore, current flow will be higher. Current flow will be higher. Current flow will be higher with higher number of current flow will be higher with higher number of ionized atoms. With higher number of ionized atoms. With higher number of ionized atoms. Ionized atoms. Within brackets, electrons. Within brackets, electrons. Within brackets, electrons. Right. Then mention this. Therefore, when temperature increases, I increases, both R rho decreases. Mention this way, like this. In red, when temperature increases, I increases, R and rho decreases. R and rho decreases. Right. Now for this also, we have an equation. So below this, you can mention the equation. R theta equals R naught 1 minus alpha theta. Right. Same equation, 1 minus. Mention this. R theta equals R naught 1 minus alpha theta. Right. No need to introduce terms again. Same. R theta equals R naught 1 minus alpha theta. Right. R theta equals R naught 1 minus alpha theta. Right. For conductors 1 plus alpha theta. Semiconductors 1 minus alpha theta. Right. So how do non-ionized particles become ionized particles? By increasing temperature. Right. So before I answer your question, first tell me whether you do chemistry or ICT. ICT, that's the thing. There's a little bit chemistry part there. So what happens is, uh, when heat is applied, heat is an energy, right? When the energy is applied, uh, ionized particles are the free atoms, free electrons, right? They can absorb that additional energy, right? And if that additional energy exceeded the energy in that bond, that bond will be broken. After the bond is broken, they will become free atoms, right? They have some kind of a potential energy for the non-ionized particle, right? When we are giving the heat, when the heat is applied, it absorbs that heat, and once that potential energy is exceeded, it becomes some additional kinetic energy. Then it becomes free. That's how free electrons are coming, right? That is called thermal ionization in chemistry. That is called thermal ionization in chemistry. Uh, I don't know whether that's there for A-level chemistry. Do you have thermal ionization in A-level chemistry? Can anyone confirm? I can't remember, that's why. I did chemistry, I can't remember. Do you have thermal ionization in chemistry? Thermal ionization. Do you know the? Yes, okay. Then that's it. Thermal ionization. Always atoms can absorb heat and ionize. Right? ඒගොල්ලන්ගේ අර stick වෙලා තියෙන bonds කඩා ගන්න පුළුවන්. They can break their bonds and they can behave as free atoms, free electrons, as ionized electrons. Thermal ionization. Right? I mean, we don't have like into that detail in physics here because both chemistry and ICT students are here, right? But in chemistry, I think you are learning it as thermal ionization. Okay. Arne, let's move on. Third one, insulators. Insulators. Insulators, third one. Insulators. Listen. Look at the board. Here, what happens is something like this. Right? They also decrease, but slightly decrease like this. Decreasing slightly. It has a slight decrease. The reason is this. The reason is this. Listen. When it comes to insulators, right? Their atoms are, right? Almost all atoms are non-ionized in the natural state, right? That is why they are being insulators. The atoms are, almost all atoms are non-ionized in the natural state. When temperature is increasing, when heat is applied, when temperature increases, some of the non-ionized atoms, right, will be ionized. A few, very few of ionized atoms will be ionized, right, using that energy supplied with the heat, right? Therefore, it increases its conductivity by a little bit, right? When the conductivity increases by a bit, then current flow increases by a bit. Then resistance and resistivity decreases by a bit, right? Take it down. Take down the graph. Take it down. right? Okay, measure in point form. First point, first point, first point. Almost all atoms, almost all atoms, almost all atoms are non-ionized. 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 In insulators, in insulators, in insulators, in insulators, in their natural state, in insulators, in their insulators, in their natural state, in insulators, in their natural state. Second point, when temperature increases, when temperature increases, when temperature increases, non-ionized particles are, when temperature increases, non-ionized particles are, non-ionized particles are slightly becoming ionized. Non-ionized particles are slightly, non-ionized particles are slightly becoming ionized. Non-ionized particles are slightly becoming ionized. Slightly becoming ionized. Next point. Next point. It results in. It results in. It results in. It results in having a few. It results in having a few. It results in having a few ionized atoms. It results in having a few ionized atoms. Having a few ionized atoms within brackets electrons, within brackets electrons, within brackets electrons, and it causes, and it causes, and it causes, and it causes, and it causes a slight current flow, and it causes a slight current flow, and it causes a slight current flow. Right. See, therefore, this is what happens now. When temperature increases, current flow slightly increases. I use dotted lines here. Current flow slightly increases, like very weak, slightly increases, and both R and rho slightly decreases. Right? Mention in red. Mention in red. Mention in red. Right? There are no equations. There are no equations for insulators. Right? There are no equations for insulators. That's a very slight, a weak decrease. No equations. Right. Then for superconductors. 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 Look at the board. Right? Superconductors are also conductors. Listen. Superconductors are also conductors. They behave as conductors. Listen. They behave as conductors in some temperature range. They behave as conductors in some temperature range. And at some point, when temperature decreases, at some point when temperature decreases, its resistance becomes zero at once. Its resistance becomes zero at once. At some point. That always happens when decrease in temperature for some metal here, for some metal, they have negative values as well. It can be either positive or negative. That temperature that is becoming superconduction, right? That can be either positive or negative, but that is a small value, a small temperature. When temperature decreases at some point, suddenly its resistance becomes zero, but yet current is flowing. Current is flowing. When resistance becomes zero, which means the disturbance for current is zero here, because resistance was the disturbance of current, disturbance for current. When disturbance for current is zero, conductivity is super high, right? Because they were inverse. When resistance is zero, right, current should be super high. That's why they are called superconductors, right? That's why they are called superconductors, because if we can have a state like resistance zero, that's the ideal scenario. That's the best scenario. That's the best scenario, because there's no disturbance at all for the flowing current, right? That is called superconductors, and most of the metals are behaving as superconductors, like aluminum, copper. They behave as superconductors, but not all the metal, but most of them. Right now, here the beauty is it behaves as a conductor for some region. Now this is a conductor for this part. Right now here it behaves as a conductor, and this range it behaves as a superconductor. Right, so only this range is a superconductivity property, but this is how overall a superconductor behaves. It behaves as a conductor, as a normal conductor in this region, just as a normal conductor. But at some point when temperature decreases, rho and R becomes zero at once, right? Suddenly, immediately it becomes zero. Take it down first. But in the conductor graph, the arrow was going up. Same. Even when the temperature increases, decreases, it behaves same in the conductor part, right? That's why increasing curve is drawn. Otherwise, if the decreasing one is drawn for a conductor, there's a possibility of behaving it as a superconductor when temperature decreases. Explain again, right? Take it down first. This is not a behavior every metal has. This is not a behavior every metal has. But most of them, right? Listen. So when we decrease temperature from, say, starting from room temperature, we decrease temperature, cooling. We are cooling this, right? When it decreases, resistance and resistivity decreases. So just as a conductor, right? But at some point, right, in a small temperature, and sometimes it can be a negative temperature, suddenly it becomes zero. Resistance becomes zero, right? Suddenly resistance becomes zero. When we do an experiment using ammeters and ohm meters, right? That's how these things are observed, right? We have things to measure them, then resistance becomes 0, right? When resistance becomes 0, I increases. That's a maximum stage of conductivity. If resistance is 0, if there's no resistance at all, right? That behavior is called superconductivity. That behavior is called superconductivity. Questions? Why we discuss about decrease in temperature only in superconductor? Because listen, that's also a good question. Listen, because superconductivity is achieved when decrease in temperature, right? Because superconductivity is achieved when decrease in temperature in reality. Because usually any substance is at which temperature? Room temperature. No? If I have copper, my copper is at room temperature. No? If I have aluminium, that is at room temperature. Then it should decrease until it gets superconductivity, right? That's why. Right? First point. First point. Superconductors behave as normal conductors. Superconductors behave as normal conductors in some temperature range. 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 Next point. But when temperature decreases, but when temperature decreases, but when temperature decreases, but when temperature decreases, at some point, at some point, at some point, its resistance, at some point, its resistance suddenly becomes zero. Its resistance suddenly becomes zero. Its resistance suddenly becomes zero. And current keeps flowing. And current keeps flowing. And current keeps flowing. And current keeps flowing without a potential difference. And current keeps flowing without a potential difference. And current keeps flowing without a potential difference. Current keeps flowing without a potential difference. Therefore, when temperature increases, right, current rapidly increases. Current rapidly increases. Both R and rho rapidly decreases. Right? Mention this in red. When theta increases, current rapidly increases, and R rho rapidly decreases. It's zero actually. Right? Mention in red. Mention in red. Right. So when temperature decreases, do ionizing particles become non-ionized? Yes, it does up to some extent. It does up to some extent. It does up to here. Then, so at first, most of the atoms are ionized. It is ionized naturally because that's a conductor. It's a conductor in natural state. Superconductivity is only in a given specific temperature range. Right? Now, as an example, take copper. Right? In some temperature range, it behaves as the normal conductor. Right? And close to zero, there are temperatures. Right? It behaves as a superconductor. Same metal, same metal. It is a property which has in a specific temperature range. It is a property we have in a specific temperature range. Okay, right. You said temperature increasing. I didn't get your question. When temperature decreases, R becomes zero at a point. Downward arrows. When temperature decreases, R becomes zero at a point. Right. So before moving on to the next, any other questions? Anything to clarify? Sorry. Thank you. Sorry. When temperature decreases, yes. Sorry. Right. Sorry. When temperature decreases, I increases rapidly, R rho decreases rapidly. Right. Dengar. So that's better, very vigilant. Right? Yeah, temperature decreases. Sorry. Right. So any other questions from these four variations? Before moving on, we are going to move on to the next part where you will see what the relationship between resistance and resistivity is. Any other questions? Any other thing to clarify? Raise your hand if it's all clear. Raise your hand if it's all clear. YouTube ones, you also can put a thumbs up or put it to the live chat. Okay, good. Okay then, right, let's move on. Good to go. Right. As the next heading, write down relationship between resistance and resistivity. Relationship between resistance and resistivity. Relationship between resistance and resistivity. Online students, all your tunes will be received to you by the next week. I think by maybe Tuesday. Yeah, by Tuesday or next Tuesday or Wednesday, you will receive your tunes. Right? Right. Relationship between resistance and resistivity. Listen. This is a conductor. Look at the board. Say this is a conductor. This is a conductor. This is a conductor. Right? Conductor. Say its cross-sectional area is capital A. Right? Its cross-sectional area is capital A. Right? For each conductor, for any conductor, it has a resistance. It has a resistance in the material itself. It has a natural resistance in the material itself. Right? That is evaluated, that is calculated or quantified using resistivity. Then material, the quality, the substance material has is called resistivity, right? And resistivity is the constant for the material. It's a constant for the material. It's not changing with area or length or whatever it is, right? Say copper, for any copper metal, resistivity is given. Just as specific heat capacity, right? It depends on the substance only. And resistance changes. It's a variable. This is how it happens. This is how it happens. Let's say length of the conductor is L. Length of the conductor is L. The relationship is this. Resistance equals rho L over A. Resistance is given by rho L over A. Rho is the only constant here. Listen, rho is the only constant here. Both L and A are variables. When L increases, resistance increases. When A increases, resistance decreases. So likewise, A, L and rho are the A, L and R are the variables. Rho is the constant, right? So that's why I said before, R and rho behaves the same. For a given conductor, length and area are same, no? Then in that case, R and rho are proportional. That's why all the shapes are same in the previous graphs. Right, now you can see it, how it happens. This is the equation, and resistance is a variable. Resistance is a variable. Resistance of this conductor is less than resistance of a conductor of 2L, like this. Right? Resistance of this conductor is greater than 3 times of this first one. And even when the area changes like this, it changes. We will see all these things. I mean, there are more things coming up, right? We are just taking the start about resistance and resistivity. More things coming up, right? Make a relationship. This is the relationship between these two, right? So what you need to understand is resistivity is a property of being resistive. Listen, resistivity is the property of being resistive. To which extent, to which degree the resistivity is, the resistance is in the material, right? It's a constant. For aluminium, resistivity is a given value. For copper, that's a given value. For iron, that's a given value. Nickel, that's a given value. So likewise, it's a constant, but with length and cross-sectional area, resistance changes. Right. Take it down and write down the equation as well. We are going to introduce terms R, rho, L, A. Resistance and resistivity. R equals rho L over A. 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 Right. Introduce terms R, resistance. R, resistance. R, resistance. Resistance. Within brackets mention, measured in ohms. Within brackets, measured in ohms, right? This is the symbol. Measured in ohms. Measured in ohms. Resistance, measured in ohms. Measured in ohms. I'm pretty sure you have seen this in all levels. Right. Then rho, resistivity. Rho, resistivity. Rho, resistivity. Rho, resistivity. L, length of conductor. L, length of conductor. L, length of conductor. length of conductor, length of conductor, a cross sectional area, a cross sectional area, a cross sectional area, a cross sectional area, right? Again, a small task. Find units of rho. Find units of rho. Units of resistivity. Find units of resistivity. Units of resistivity. Units of resistivity. Units of resistivity. So resistivity is a constant resistance. Yeah. Yes, exactly. Ohm meters. Yes, ohm meters. Right? Rho. Rho is given by, right? Rho is given as subject rho. Units of R, units of A, units of L, right? Units of R, ohms, units of area, square meters, units of length, meters, one cancels, it is ohm meters, right? Units of rho, ohm meters, ohm meters, ohm meters, ohm meters. So if resistivity is constant at given temperature, if temperature changes, it changes. That's what we discussed in the first part, right? For a given material, at a given temperature is a constant. Right? It's better that you ask. If temperature changes, it changes. Constant at a given temperature. Ohm meters. Okay, so clear. Right, good. So that's why first of all we discuss about the variation with temperature, because it changes with temperature. Right? Now we are going to you are going to see Ohm's law in the next step, I mean next part. So in Ohm's law also it's clearly said that under constant temperature, when other conditions are constant, temperature when other conditions are constant, which means when temperature should be constant, otherwise it changes. Okay, ohm meters. Right. So write down below with a red pen. Write down below with a red pen. Write down below with a red pen. Resistivity is constant. Write down below with a red pen. resistivity is constant. Resistivity is constant. Resistivity is constant. Resistivity is constant for a given material. For a given material slash substance. For a given material slash substance at a given temperature. At a given temperature. At a given temperature. At a given temperature. Okay. Listen, a small question. Listen carefully. A small question. A small question. Listen. If my goal is to if my goal is to have a higher current flow, my goal is to have a higher current flow, right? Tell me, in terms of length and area of conductor, how should it be? If my goal is to have a higher current flow through a conductor, if my goal is to cater a higher current flow through a conductor, to have a higher current flow, to cater a higher current flow through a conductor in terms of length and area, tell me, how should them be? How should them be? Whether I'm asking, yeah, you got my question, right? Okay, because you got an answer. Yes. Good. It's clear enough, right? හැමෝටම වැඩේ තේරුණාද? Think of it. Think a little bit. And connect current and resistance and this equation. Right. Is it clear? Any different answers? So is it clear what happens there? Right. See? So we will mention this. Now if we need to, listen, first look at the board. Look at the board. If I need to cater a higher current, right? Higher current means it should be a lower resistance, no? Higher current is a lower resistance. But resistance is given by this equation. See, resistance is given by this equation. So we know R equals rho L over A. Then to decrease, to reduce resistance, so either L can be reduced or A can be increased. Either L can be reduced or A can be increased because rho is a constant. Right? A reduced L means it should be a short conductor. Right? A higher area means it should be a thick conductor. Right? So basically, to cater higher current, conductor should be short and thick. Right? Conductor should be short and thick. Think about the short and thick conductor and tell me if you have seen any examples for short thick conductors. Short thick means it carries higher current. Short thick का मतलब करेगा. Short and thick. Many cases. Right? Day to day we have. So first let's mention this. You can think of it meanwhile. Okay. Write down as an next point. To cater a higher current. Write down as the next point. To cater a higher current. To cater a higher current, to cater a higher current. During laboratory experiments to cater a higher current. During laboratory experiments to cater a higher current. During laboratory experiments to cater a higher current during laboratory experiments. To cater a higher current during laboratory experiments. Short, thick conductors. Short, thick. Short, comma, thick. Short, comma, thick conductors should be used. 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 Right. Mention this. This part. This part. This part. Mention this in red. This equation is valid only for conductors out of the four types. Yes, this is only for conductors, right? And all other equations coming up in current electricity are also for conductors, right? This is also for conductors, right? I mean, conductor and resistivity can give. This is only for conductors, and all other equations coming up in current electricity are also for conductors, because conductors are meant to be meant to flow a current, right? But first of all, to take the approach, you need to know all the differences, similarities, and those things, So that's why we discussed all background. But conductors are meant to be carrying currents, carrying electrons. Okay, right? Yeah, what are the examples? Simply, this is the idea that I need to give. Listen. Just by looking at the thickness of a conductor wire, right? We can say whether it caters a higher current or comparatively lower current, right? Now, as an example, this is a charging cable. See, this is a charging cable. This is a charging cable. A mobile phone charging cable, right? So you can see the thickness now, right? This thickness is to cater, right, to satisfy the small amount of comparatively small current which comes into the mobile phone when it is connected to the charger, right? Now, if you check a wire of a TV or sometimes a laptop charger, right, or a refrigerator connector, AC connectors, air conditioners connectors, electric motor connectors, right? The wire sizes are very thick now. That is because they absorb more current. They require more current. Then wire should be thick enough. Wire should be thick enough to satisfy that current. So simply, higher the thickness of a wire, higher the current it can carry. Higher the thickness, higher the current it can carry. Right? Now here I have another connector for this spotlight. See? Now this one is, I hope it's not visible. One second. My video might be dark because I switch the light off. See, many wires there. Now this is a wire which is connected to a spotlight. So in the spotlight, we have a LED panel, right? And this is a wire of my mobile phone charger. See, this is more thin. Black one is more thin. Black colored one is more thin, right? Which means LEDs require a small current compared to the current absorbed by the mobile phone when it charges, right? That's the idea. So likewise, you should be able to compare them with the sizes. You should be able to compare them. Okay. You should be able to compare them with the sizes, right? We can compare them with the sizes. What are the other examples for thick wires? Right? Tell me. What are the other examples you have seen for thick wires day to day? Thick wires, thick wires. Share your thoughts. Thick wires. Go thick wires like that. Roads is a good example. Now, if you can check it with that breakdown, right? Some sort of general knowledge. Tell me, what's the voltage we are getting for our households? What's the voltage we are getting for our households? Households වලට එන්නේ voltage කියලා. General knowledge, because these things are coming up, right? තව තියෙනවද? These things, these general things are also coming up. Some part is in electricity here, and another part is there in electronics also. What's the household voltage we are getting? Household voltage 230. Yes, 230, not 80. 230. Fine. Then do you know what's the voltage of a single wire in concrete columns? There are 3 wires usually, right? There are 3 wires usually. What's the voltage of one wire connected to transformers? Transformers done. No? What's the voltage of one wire connected to transformers? Wires of projectors. Yeah, that's also a correct example. Yes. Have you heard about 11,000 and 33,000? High tension lines, high tension, 33,000. අර රැප් එකක් තියෙන වද්දා ගන්න 33,000 මොකක්ද කියලා රැප් එකක් තියෙනවනේ. High tension 33,000. What's that rap? අර මොකක් රැප් එකක් තියෙනවා. Sri Lankan rap. Okay, anyways, high tension means 33,000. It goes as 311,000 wires. 311,000 wires. Right? I couldn't remember how that rap starts, but there's a rap. Something like that. Okay, 11,000 volts. High tensions. One high tension wire is 11,000. Right? Now, if you carefully observe, right, the thickness of high tension wires, they are more thick compared to the wire. These are the wires coming to the transformer, right? There's something called transformer. I think you had to step down and step up transformers in all levels, right? But even if you had or not, don't worry, because it's coming up in electronics, right? Just know that there's something called transformers. May box එකක් වගේ අර පාර දැකලා ඇති. Right? There is something like this on roads, right? Something like this. That is called a transformer. The wires which comes into the transformer are 11,000, right? They are more thick like this. They are thick, 11,000. They are thick. And the wire which is coming out to households from transformer is thin, more thin compared to this, because it carries only 230, whereas this has 11,000, right? And the wires we have in our wiring system, in-house wiring of the house, it is even smaller in the sense even thinner compared to this wire that you are getting it from CEB electricity board, right? ඒ වයරකට වඩා මේ wires පොඩි. and with respect to the device you use, and with respect to the device you need to use, and you are using with the current absorption, right? With the amount of current absorption by the device, the size of the wire changes, right? That's how it is, right? There are very small wires if that's a very small current. There are instances with very small wires if you have if the requirement is a very small current, right? We have more thick wires if the current requirement is very high, right? Projectors, hurry. Then fans, table fans, or maybe stand fans, right? Fan එක වගේ more thick. So likewise, now you always should observe these things, look at these things with this physics eye. Then you will see we can easily compare those currents. You can easily compare those currents, right? Computer cables, laptop cables, right? That's how it is. Mobile chargers are thinner. Charging cables, mobile charging cables are thinner compared to the other laptop charging cables or other heavy charging cables. Can you give me a minute? A call is coming, need to pick up. Give me a minute. Okay, right. Sorry about it. Was something urgent. Right. Okay, right. Listen. Then, so likewise, you should be able to think of those examples. In day to day, we see these things, right? Always now, when you learn this, always learn it with the practical side of it, practical physics. That's how it should be. Don't just limit it to the book. That's not the physics is. That's not what physics is. Physics is always a practical subject. That is all about what we see day to day, right? What we observe day to day, what you use day to day, right? That's how it is. Now, a charging cable of this mic is even smaller because it has only a very small current. I don't have the cable right now with me, right? It is very small because this need only a small current, I think around 0.1 amperes or something like that for this one. So likewise, with that amount of current to be passed, it changes, right? That's enough. I hope the idea is clear enough, right? Okay, any questions so far? Time for questions. Any questions so far? Any questions so far? Any questions so far? Right. Okay, no questions. We will move on as the next heading. Write down. Next heading. Drift velocity. Drift velocity. Drift. Drift velocity. Drift velocity. Drift velocity. Drift velocity. Listen. Listen. This is the idea. Listen. When current passes through a conductor, we know electron flows. No? Electrons flow. Electrons flow. When electrons flow through the conductor, since it has a certain resistance, right? It is not free flowing. It is not freely flowing. It drifts, right? So you know the meaning drift, right? Drifting කියලා කියන්නේ ඔය සමහරවිට in race, I mean supercars, maybe high speed motor show, so drift කරනවා කියලා කියන්නේ, you know, right? That's not a smooth flow, but it drifts. So what happens is electrons are not freely flowing just as a fluid. එහෙම flow වෙන්නේ නැහැ. It is not flowing as a fluid. That is not as free as that. So it has some kind of a disturbance, some kind of a resistance. Therefore, electrons drift along the material. Electrons drift, right? They drift. So we are going to find that velocity. The electrons are drifting through the material, right? Write down below. Write down below. When current flows, electrons flow. When current flows, electrons flow. When current flows, electrons flow to the opposite direction of current. Electrons flow to the opposite direction. Electrons flow to the opposite direction of current. Electrons flow to the opposite direction of current. Electrons flow to the opposite direction of current. Opposite direction of current. Next point. Since substance has a resistance, a certain resistance. Since substance has 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 a certain resistance, electrons drift along the material, drift along the substance. Electrons drift along the material. Electrons drift along the material slash substance. Electrons drift along the material slash substance. Right. Listen, look at the board. Say this is a conductor now. Say this is a conductor and it carries a current I. Say it carries a current I. It carries a current I. The flow of electrons is opposite. Flow of electrons is opposite like this. Flow of electrons is opposite like this. Right? Listen, another important idea. For any substance, for any material, it has a given number of electrons in a unit area. It has a given number of electrons in a unit area. Right? A given number of electrons in a unit area. That is called electron density. That is called electron density. That is called electron density. Listen, that is called electron density. Because different materials has different compositions of electrons. Different conductors have different compositions of electrons. Electron density. Electron density is number of electrons. මේකට අපි දාන්නේ capital N. This is capital N. Electron density, capital N. That means number of electrons per unit volume. Electron density. It's given for a material. For copper, we have a certain electron density. For aluminium, we have a certain electron density. For iron, a certain electron density. Right? Because that is about the composition of the substance. No? That is called electron density. Keep that in mind. Right. Now, for this material, let's assume electron density as N. Let's assume electron density as N. Right? Saying again, explaining again, electron density is the number of electrons per unit volume. This is volume. Number of electrons per unit volume. Right? This is number of electrons number of electrons per unit volume. Number of electrons per unit volume. Right. So first of all, before taking this down, take this down. Write down electron density. N equals NOV. Write down this one. Don't take down the diagram. This one. Take down this one. Electron density, capital N, is simple NOV, number of electrons over volume. Take it down. Take it down. Right. Write down below. This is the definition in red. Write down the definition in red. Number of electrons per unit volume. 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 Number of electrons per unit volume is defined as electron density. 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 Right, that's the definition. Next point. Next point. Electron density is a constant for a given substance. Electron density is a constant for a given substance. Electron density is a constant for a given substance. Electron density is a constant for a given substance. Electron density is a constant for a given substance. Listen now. Listen. Right, now let's assume electron density of this substance here as N. Electron density is N. Right. So that means there are simple N number of electrons in this conductor per unit volume. Right. Okay. So let's assume area of this conductor as capital A. Now look at the board. Area of conductor is A and length of conductor as L. Length of conductor as L. Right. Listen now. By definition, you know, listen, and you have to prove this. Right. You will have to prove this. Questionable. You will have to prove this. Right. Look at the board. Questionable. I equals Q over D by the definition. No. I equals Q over D by the definition. I equals Q over D by the definition. Right. I equals Q over D by the definition. Then we know I can also be written as Ne over T. No. Number of electrons, charge of an electron over time. Ne over T. Right. Now see what's happening about this material. In this material, there are capital N number of electrons, electron density. There are capital N number of electrons per unit volume. Per unit volume. Then if I multiply this value by the volume of conductor, I can get the total electrons, total number of electrons in this conductor. No? Because this is the number of electrons, capital N. Capital N is the number of electrons per unit volume. Right? Number of electrons per unit volume into the volume of conductor gives the number of electrons, total number of electrons in this conductor I have selected. No? Right? See, then I'm going to plug for this. See, if I need total number of electrons here, it should be number of electrons per unit volume. That is electron density into volume. Volume of this conductor is AL. No? Volume of this conductor is AL. Cross-sectional area into length. Volume of the conductor is AL. Right? Then N should be NaL. N should be NaL. Right. Then I equals, right? Instead of N, I can use capital N AL times E over T. Right? Right. Now, we know, look at the board. Velocity is change of displacement over time. No? Now, change of displacement of an electron during this time is from t equals 0 here to t equals t here, change of displacement of an electron. during this time is L, no, because electrons flow from here to here, from one end to the other. Then displacement is L, change of displacement is L. Then L over T gives us velocity, right? We have L over T here already, see? We have L over T here. Let me isolate this. Then this can be written as NAE times L over T, no? L over T is velocity of an electron. Velocity of an electron is called drift velocity, right? Velocity of an electron is called drift velocity. Then we can plug drift velocity here. Then I equals NAE. This is called VD, drift velocity. VD, drift velocity, right? Drift velocity. Then final equation is, right? For our is, this is how we keep this equation in mind. For our is I equals NE, right? And usually for the ease of recalling, remembering, memorizing the equation, right? For the purpose of memorizing the equation, we usually call this I equals Vane. I equals Vane. VANE. I equals Vane. V is VD, right? V can VD, but for the ease of what is drift? That's what my first question before explaining drift velocity, right? That was my very first question, right? So I equals Vane. We call I equals Vane, right? There are these kind of like these type of equations, more equations coming up in electricity and magnetic fields also, like uh, G equals beta, I equals Vane, band omega, different ones are there. So this is called usually we call I equals Vane, right? V is VD, right? Forget about D for a moment because our intention is memorizing. For the memorizing purpose, this is called I equals Vane. Equation of drift velocity, right? Equation of drift velocity, where I is current, V drift velocity, A cross sectional area, N electron density, E charge of an electron, right? And this is questionable. You should be able to prove this by your own, right? Start from here and prove this. We'll be introducing terms here. I, VD, A, N, E. Drifting means that's not a free flow. Drifting means uh, it's like drags around the material. Drags along the material. It drags. That is called drifting. Drags along the material, right? So as a result of this, since it drifts in the material, heat is also generated. So we will see heat dissipation when the current flows. So therefore, when the current flows, there's a heat generation as well. That is called heat dissipation, right? So everything is there under current electricity. You will see in the coming up weeks, everything will be rolling out in the coming weeks. Take this down. Through it. Drifting is always opposite to current flow. That is because electrons are negative charges. That is coming from electric fields. Negative charges accelerate opposite to the direction of current flow. Positive charges accelerate to the direction of current flow. Negative charges accelerate to the opposite direction of current flow. Electric fields. Everything is connected. Everything is connected. Rho is a sign of resistivity. Why you waited so long to ask that question? 9:15. I think I started the discussion with Rho. Why you waited 2 hours and 15 minutes to ask that question? What was Rho you have been writing from the beginning? Arkam, what happened? By the way, did you mistake E and Rho? I'm just guessing. This is E. Q equals NE. This is E, not Rho. I'm just wondering whether you have mistaken E with Rho. I just had a small doubt. This is E. Q equals NE. Okay, finished. Introduce terms. Introduce terms. You have to understand what we do here because you should be able to prove this by your own. Should be able to prove this. Right? Should be able to prove this. Introduce terms I electric current, I electric current, I electric current, VD drift velocity, VD drift velocity, VD drift velocity, VD drift velocity, A cross sectional area, A cross sectional area, A cross sectional area, N electron density, N electron density, N electron density, capital N electron density, capital N electron density, simply charge of an electron, simply charge of an electron, simply charge of an electron, charge of an electron, charge of an electron. Right. Okay. Let's move on. Right. So you can keep this in mind. You can memorize this equation as I equals when A. Right. In can you remember in properties of in matter and radiation we discussed E equals eta, E equals eta. So just like that, this is I equals when A. Right. I equals when A, E equals eta. Right. Very easy, no? To memorize. Okay. Let's move on. Next, in Ohm's law. Ohm's law. Ohm's law. Ohm's law. Ohm's law. Listen. Listen. When comes to listen carefully. When comes to conductors, right? A conductor which carries a current, right? To carry a current, we have to have something called a potential difference. A potential difference. If I compare this with the things you already know, when a fluid flows, we know fluid flows from high pressure to low pressure. No? Fluid flows from high pressure to low pressure. Very comparative cases. And heat flows from high temperature to low temperature, right? And force due to pressure difference exerts from high pressure to low pressure, right? So just as that, current flows from high potential to low potential. Potential is also called voltage. Potential is also called voltage. So current flows from high potential to low potential, or I can say high voltage to low voltage. Voltage is, listen very carefully, voltage or potential is a property, an attribute the conductor has, a point of a conductor has, right? It is an attribute a point of a conductor has. And the definition of electrical potential is exactly same as what we have in electric fields. Exactly same. Actually, it is coming from electric fields, right? In electric fields, we define electric potential as the amount of work to be done to take a charge from infinity to take a unit charge from infinity to point in an electric field. No? Same thing, right? That is called the potential, electrical potential. Same thing is going to be used here. Electrical potential or potential at a point in an electric field. Amount of work to be done to take a charge from a unit charge from infinity to point at the electric field, right? Same thing, right? Now, for here, only thing you need to know is potential is a feature, an attribute at a point of the conductor. That is at a point of the conductor, right? When potential difference is there only, current flows, because current flows from high potential to low potential. Current flows from high voltage to low voltage, high potential to low potential, right? Now, in Ohm's law, let's assume this is a conductor. So here, let's assume this is a conductor. This is a conductor. This is a conductor, right? And let's say potential at this point is VA. We use V for the standard symbol as a standard symbol of potential, V, right? VA, just as electric fields, and VB, let's say, right? Potentials are VA and VB. Potentials are VA and VB. If VA is greater than VB, listen very carefully. If VA is greater than VB, current flows from VA to VB. If VA is greater than VB, current flows from VA to VB. Right? What Ohm found was, Ohm is the name of the scientist who found this, right? What he found was potential difference across the ends of the conductor is proportional to the current it carries, right? Which means higher the potential difference, higher the current flow. For a given conductor, higher the potential difference, higher the current flow. For a given conductor, right? So otherwise, don't say if area changes, if length changes, then it changes, right? For a given conductor, right? Under given temperature, when potential difference increases, right, I increases. When potential difference increases, I increases, right? So if I simplify this, if I make it simple to you to understand further, right? You know batteries, cells, batteries is what we have to supply a potential difference to a circuit, right? Now, if I connect a conductor to a battery, it supplies a potential difference across the conductor. So simply, batteries are to supply a potential difference to the conductor. Batteries, right? So you are buying from maybe supermarkets, food series, right? Or wherever batteries, you know, any type of battery, right? Batteries are supplying potential differences. right? Okay, now if I need to increase potential difference here, voltage of the battery should be increased. Simple as that. What Ohm found was potential difference across, that is delta V, yeah? Potential difference is delta, no? Delta V, potential difference across the two ends of conductor is proportional to the current it carries. It is proportional to the current it carries, right? This law is called Ohm's law because it was found by the scientist whose name was Ohm. And as an honor to this, right, something was uh, labeled as ohms, that you know already, resistance, right? We'll see how it links to here, right? This is called Ohm's law. This is called Ohm's law. Potential difference across a conductor is proportional to electric current flows through the conductor when other conditions remains constant. When other conditions remains constant, other conditions means all the dimensions of conductor and most importantly the temperature, right? Other dimensions and the temperature, because you already know now with the temperature and with the dimensions, resistance changes, right? So let's see how resistance is linked to here. Right, take this down and write this down. This one, this is the law. First we will mention the law and then I'll explain further. Take it down. But doesn't a battery have fixed voltage? No, that's a voltage difference, not a voltage. That's a voltage difference. That's why it has plus minus terminals. Can you repeat the labelings for NA? V drift velocity, A cross-sectional area, N electron density, E charge of an electron. Understand these fundamental concepts, right? Understand these fundamental concepts, right? Very important. This is the foundation. I told you from the very beginning. This is the foundation. This is the foundation. And laws like Ohm's law is playing a major role, like around 50% in electricity is played by Ohm's law, right? Connected to everywhere in electricity, starting from here, connected to everywhere. Finished? Okay. Write down Ohm's law in red. This is the law. This is called Ohm's law. Mention it in red. Mention it in red. Write down. Write down in red. Electric current flows through a conductor. Write down. Electric current flows through a conductor. Electric current flows through a conductor. Electric current flows through a conductor is directly proportional to electric current flows through a conductor is directly proportional to electric current flows through a conductor is directly proportional to potential difference 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 across conductor. Potential difference across conductor. Potential difference across conductor when all other conditions remain unchanged. 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 Underline, no highlight. Underline, no highlight. When all other conditions remain unchanged. Underline, no highlight. When all other conditions remain unchanged. Underline, no highlight. When all other conditions remain unchanged. When all other conditions remain unchanged. Right. Listen now. Look at the board again. Right. Look at the board again. From Ohm's law. See. From Ohm's law, we know, look at the board, delta V is proportional to I now. We know to make this an equation, we need a constant of proportionality. To make this an equation, we need a constant of proportionality. As the constant of proportionality, Ohm introduced resistance, right? Then with the resistance, he stated the equation as delta V equals Ri. Delta V equals Ri, right? Now you all know that resistance changes with temperature. Resistance changes with length of conductor and resistance changes with area of conductor, which means all other conditions means especially these three conditions of the conductor should remain same when we apply this equation, Ohm's equation, right? And he stated the equation as delta V equals IR. Delta V equals IR. Delta V equals IR, right? Sometimes you might have learned this equation, same equation as V equals IR, right? That is not V, that is wrong, right? Now you have to upgrade to yourself. That is not V, that is delta V. Delta V equals IR. Potential difference equals IR. Not the potential, right? Very important. Potential kya neka? Potential difference kya neka? So don't write V equals IR again, right? Get used right, delta V equals IR. Get used right, delta V equals IR, right? So I gave you the exact thing. Even if you are writing V equals IR, keep in mind carefully that V is not a potential, that's a potential difference, right? There are some students who are writing V equals IR just for the ease of writing the equation, right? But if you mistake the idea here, right, you are not going to get correct answers or you are not going to succeed in the applications coming up, right? So this is the safe way. This is the exact thing actually. Safe name. This is the exact thing. In O levels, you have learned something different because that was O levels, right? Now you have to upgrade yourself. You are way matured now, right? You are way matured now. 28 batch is already started. You are the oldest now, right? You are matured. Oldest means you are matured. So that is not V equals IR anymore. That is delta V equals IR. Delta V equals IR. Where delta V is potential difference, right? Because this is coming from Ohm's law. Delta V equals potential difference I, electric current, R, resistance of conductor, resistance. Right, okay. Start from here and prove the equation. Start from here and prove this equation. Start from here and prove the equation. Can you repeat? Repeat what? So if you know something regarding the note, if someone saw the question, feel free to help each other, right? You are the same batch, no? I didn't see. What was it? First point, I didn't give any points. What do you mean? Yeah, which point do you mean? I didn't get it. Otherwise, I would repeat. Which point do you mean? Take this down. Sorry. From Ohm's law, delta V equals I. Constant of proportionality is R. Right? Constant of proportionality, listen, constant of proportionality remains constant when these conditions are constant only. When other conditions means dimensions, area, length, and temperature. Right? Because this is the proportionality constant of the equation. Right? If anything out of temperature, length, or area of the conductor changes, this equation is invalid. This equation is invalid. Right? This is only for a given conductor at a constant temperature. Right? Otherwise, Ohm's law is not valid. Right? Finished. Introduce terms delta V potential difference. Delta V potential difference. Delta V potential difference slash voltage difference. Delta V potential difference slash voltage difference. Delta V potential difference slash voltage difference. I electric current. I electric current. I electric current. R resistance. R resistance. R resistance. R resistance. Right. Listen now. Listen. More interesting facts. Listen. More interesting facts and very significant things. Listen. 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 Now, when we draw circuits, listen. When we draw circuits, we are using conducting wires to connect circuits. No, conducting wires. Right. In A-level physics. In A-level physics, resistance of conducting wires are neglected. In A-level physics, resistance of conducting wires are neglected. In conducting wires, wires, circuit connected wires, they are neglected in A-level physics. In reality, it has a small resistance. In A-levels, it is neglected. Right? That is one thing. That is one thing. Right? Now, since resistance is neglected, listen. First, write this down. Mention karana. Take this down as a note in red. Take this down as a note in red. Take this down as a note in red. Write down first point. First point. Resistance of. Write down resistance of conductor wires. Resistance of conductor wires. Conductor wires in circuits. Resistance of first point. First point. Resistance of conductor wires. Resistance of conductor wires in circuits. Resistance of conductor wires in circuits. Resistance of conductor wires in circuits are neglected. Resistance of conductor wires in circuits are neglected. Resistance of conductor wires in circuits are neglected. Okay, look at here. See what happens when resistance is 0. See, according to delta V equals IR. See, we know delta V equals IR. Delta V equals IR. Now, if resistance is 0, because resistance is neglected now, then if, see what happens. If R becomes 0, right hand side becomes 0, delta V equals I into 0, I times 0, then delta V equals 0. What's the meaning? There's no potential difference. There's no potential difference. Right? Then if this is a conducting wire, see, if this is a conducting wire, see, if this is a conducting wire, now according to this result, there should not be a potential difference across a conducting wire. There should not be a potential difference across a conducting wire. Then, if potential of this point of the wire is say VA, if potential of this point of the wire is VA, 1 second, hold up, 1 second. Right. If potential of this point of this conductor wire is VA, if there is no potential difference, right, which means potential at any point of this wire should be same, no? Right? If the potential difference is zero, there's no difference. There's no difference. If this is A, then all along this wire, at any point along the wire, it remains as VA. It remains as VA, right? Very important fundamental concepts, right? It causes this, right? This causes due to this, right? This causes due to this, right? This causes due to this. So when resistance is neglected, delta V becomes zero. There's no potential difference. Since there's no potential difference, right? Potential at the point should be equal, right? Not to have a difference. Raise your hand if this idea is clear. Raise your hand if this idea is clear. Okay, right? Take this down. Take this down. Take it down with the diagram. Right? Very important concepts where whole electricity is driven by these things. Whole electricity is driven by all these fundamental concepts, right? The core of here is these things, core of electricity. And once you know the fundamentals, building upon this is not as difficult as understanding these things. This is also not difficult, right? But when you have these things as a solid knowledge, very easy to build up. Because everything is connected, no, that's a beauty here, right? That's what it makes is more convenient when we study, when we proceed actually, right? In a conductor, obviously, see, this is a conductor. This is only for conducting wires. This is a conductor. Even in reality, conducting wires has a very small resistance. In reality, conducting wires has a very small resistance. For A-level physics calculations, we neglect it because that's a very small value. Okay, finish. Can you explain again, please? Okay, listen quickly. If there is no resistance for a conducting wire, right? If there is no resistance for a conducting wire, then according to this result, R is 0, R equals 0. If R equals 0, delta V equals 0. No potential difference. If there is no difference, then potential at any point should be equal. There is no difference, right? Simple as that. This is for conducting wires, only for conducting wires, right? Clear? Right, which means potential at any point of a conducting wire is same. Next point, mention this as a next point. Hence, mention as the next point in red, hence, potential at any point of the same conducting wire. Then, sorry, hence, potential at any point. Hence, potential at any point. Hence, potential at any point. Hence, potential at any point of same conducting wire, remains unchanged, remains unchanged, remains unchanged, remains unchanged, remains unchanged. Potential at any point along the conducting wire remains unchanged, right? Why there is a difference in delta V in a conductor? Difference in delta V is because a difference is given by a battery, by an external source. That's given. Natural difference that should be something given from a source outside, simply a battery, right? Then next idea, listen. Now, even though there is no potential difference across a conducting wire, right, across any electronic device, or we call electronic appliance. What are the electronic appliances we have? Resistors, bulbs, LED, diodes, op amps, transistors, right? Those are electronic appliances, devices, electronic device. Across any electronic device, there's a potential difference. There's a non-zero potential difference, right? Then when you meet an electronic device, right, we can't say potential difference at the terminals of electronic device are equal. No, always it has a potential difference, right? Then through the conducting wires only, along the conducting wires only, there's no potential difference. As the next point mention this, I will show this with an example. Hold on, I will show this with an example. Next point, write down. Next point. Potential at a point changes. 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 Use red, use red, keep using red. Potential at a point changes. Potential at a point changes. Potential at a point changes when an electronic device, when an electronic device, when an electronic device, when an electronic device slash appliance is crossed, is crossed, is crossed, is crossed, right? Is crossed, right? Next point and the last point under this note, keep using red. Last point under this note, last point. Potential difference across A and B, capital A and B, write down. Last point. Potential difference across A and B. Potential difference across A and B. Potential difference across A and B. Potential difference across A and B is denoted as follows. Potential difference across A and B is denoted. Potential difference across A and B is denoted as follows. Potential difference across A and B is denoted as follows. Look at the board. Potential difference across A and B. There are two ways of writing this. There are two ways. First one is delta V AB. Potential difference across A and B. Delta V AB. Right? This can also be written as VAB. This can also be written as VAB. Standard notations are delta VAB or VAB. And this is expanded as VA minus VB. This is expanded as VA minus VB. Potential difference across A and B. Delta VAB or VAB. Right? Make an O. Delta VAB or VAB. Right? It is expanded as VA minus VB. Potential at A minus potential at B. Simple idea. Take it down. Take it down. Take it down. Simple idea. Take it down. Right. Now, look at the board. Right. So after taking this down, note is finished. You can close that note and look at here. Let's see with this with an example. See. Let's see this with an example. Right. Look at here. Look at here. This is a simple circuit. See. This is an example. This is a simple circuit. A simple circuit. This is a simple circuit. Say this is a resistor. You know, all of you know the circuit symbol of a resistor, right? This is a circuit symbol of a resistor. And this is a battery, a cell. This is a circuit symbol of a cell, right? So this is a simple circuit where a resistor of say 10 ohms resistor of 10 ohms is connected to a battery of say voltage 8 volts. You have a battery of 8 volts, 3 volts, anything, 3 volts. So you know how to identify terminals of a battery, right? Shorter one is the negative terminal and this one is the positive terminal. Positive and negative. It has two terminals, right? Listen. It has two terminals as positive and negative, right? Even if you purchase a battery from a shop, you can see positive and negative terminals are labeled there, right? Positive and negative terminals are labeled. Positive and negative. Since they are positive and negative, they have two different potentials at the terminals, which means that there is not a potential across a battery. That's a potential difference across a battery. That's a potential difference across a battery. Listen carefully, right? This is a simple example of what you learned so far in Ohm's law, right? That's a potential difference across a battery. When you purchase a battery from supermarket, say it is labeled as 1.5 volts, that is not about a potential, that is about a potential difference, right? That is about a potential difference, right? And the exact idea is there is not actually a potential difference as well, right? That is actually called electromotive force that is coming up on the batteries. But for now, knowing it as a potential difference is enough. You will get to know the difference between potential difference and electromotive force of a battery in the third week. Right? So until then, it's totally fine. Just think of the value of a battery as a voltage difference or a potential difference, right? There is a potential difference, but there's a small difference with the electromotive force. Forget about it now. If you have heard about the word electromotive force, forget about it for a moment until we are reaching cell combinations and cells, right? Okay, now say this is 3 volts, this is 3 volts. Plus and minus terminals means there is not a potential, that's a potential difference. So let's assume, look at the board very carefully, let's assume potential at this point is A and potential at this point is B, right? And all these connectors are conducting wires, no? These are the conducting wires. Listen carefully. These are the conducting wires. The median conducting wires all the way from here to here. These parts are conducting wires, and the battery and the resistor are electronic devices. Battery and the resistor are electronic devices, whereas all the connectors are conducting wires. Right? Raise your hand if it is clear so far. Right? When a circuit is given, that is how it is given, na? Right? The rest except electronic devices are all conducting wires. The rest except electronic devices are conducting wires. Right? Now, we know there's no potential difference along a conducting wire. No? If there's no potential difference, if this point is A, right? If this point is A, all the points along this conducting wire is A. All the points along the conducting wire, I, all of them I. Then if you put here, that's also A. All the way, there are infinite points, all of them are A, which means ultimately this point is also A. Raise your hand again if it is clear. And similarly, if this is B, this is through a conducting wire, this becomes B. Right. Let me explain again. Now from this you know, there's no potential difference across a conducting wire. Right? There's no potential difference across a conducting wire. Understand these simple concepts in a simple manner because I'm explaining this in the most simplest manner. Right? You will you won't ever receive more simply explanation for this than this. I'm pretty sure. Right? Mechara simple make explain karna. Listen. This is very much important. That's why I'm spending more time on this, because understanding Ohm's law and these concepts is mandatory. More than 50%, actually, not even 50, more than 50% of what is coming up is depending on Ohm's law. That is totally on Ohm's law, right? There are more things, but more than 50% is on Ohm's law. Understanding these small concepts is very much important, right? Minor things, but matters most. They matter most, right? You won't ever get a simpler explanation than this, right? Listen very carefully. Now, according to this, we know, right? There's no potential difference across a conducting wire. If there's no potential difference, the potential remains same, right? Potential remains same. In current electricity, we denote potential by the name of the point itself, right? By the name of the point itself. VA කියලා දානවා, but putting A is also enough. දැන් මම මේ circuit එකේ A විතරයි දැම්මේ. Right? We can put A or VA. Labeling means that is about the potential in current electricity. Right? Current electricity වල V දදා ඉන්නෙත් නැහැ. We are just putting same points at same labels. Same points means same points in terms of potential. Now, through a conducting wire, there's no potential difference. Then potential remains same. If potential at this point is A, since there's no difference, all the way up to this point, the potential remains as A, right? And since potential at this point is B, all the way along this conductor up to here, this potential remains as B, right? And this is an electronic device. There's a potential difference, different A and B. This is also an electronic device. There's a potential difference A and B, right? So likewise, that is how we deal with circuits here, right? This is a very simple and the simplest circuit you will ever see. A simple circuit, very simple circuit, right? To get these fundamental concepts, to understand these fundamental concepts, raise your hand again, everyone, if this is clear enough. Okay, right, listen now. Now, for this resistor, I'm going to use delta V equals IR. Listen, for this resistor, because it has resistance, no? We can use delta V equals IR. Look at the board. For resistor, delta V equals IR. Listen. This terminal, this end of the resistor is connected to A. This end of the resistor is connected to B, right? This end of the resistor is connected to A and this end of the resistor is connected to B. Then potential at this point is VA. Potential at this point is VB. Then what is the potential difference across this resistor? And now fundamentally, because of the battery, terminal positive terminals voltage is, so the potential is higher, right? Fundamentally, yeah, A minus B. Fundamentally from a battery, that is how the battery is made, right? Positive terminal is higher, positive and negative. Then positive terminal is having a higher voltage, higher potential, right? So therefore, A is a higher potential, right? Then delta V across the resistor should be one end is at A, the other end is at B. Potential at A is VA, potential at B is VB. Then the potential difference across the resistor is VA minus VB. VA is higher because A is the positive terminal. So this is VA minus VB. Right? Equals IR. Right? One more thing, listen carefully, very important. If we have a single battery, current always flows out from positive terminal because current flows from high voltage, low voltage. No? High voltage is here, low voltage is here. Then current circulates from high voltage terminal to low voltage terminal like this, right? Current circulates from high voltage to low voltage in the external circuit. The high voltage එක මෙහෙන තියෙන circuit එකේ. ඒතොර current එකට A to B යන්න බෑ. මෙහෙම යන්න බෑ. මේ rightwards යන්න බෑ. It flows as here because high voltage is at this point, low voltage is at this point of the circuit. Then current flows out from the positive terminal. Say that is I. This is how this current flows. Right? Current circulates. Right? Listen carefully. Now we have VA minus VB. No? VA minus VB. From the battery, it also has VA minus VB. Potential difference of positive terminal is VA. Potential of positive terminal is VA. And potential at negative terminal is VB. potential difference across the battery is VA minus VB. That is also VA minus VB. That is what is given as potential of the battery, or the potential difference of the battery, which means from battery, see, from battery, VA minus VB equals 3 volts. VA minus VB equals 3 volts, because always potential difference across the battery is equal to potential at positive terminal minus potential at negative terminal. Potential at positive minus potential at negative. Potential across the battery. Right? Now it says VA minus VB is 3, which means this is also VA minus VB, that is 3. Plug it here. 3 volts. 3 volts. Current flows is I, and resistance is given 10 ohms. Right? Which means current flows through the circuit is 0.3 amperes. Right? Simply, this is how we use delta V equals IR, Ohm's law. This is how we apply Ohm's law. Right? This is how we apply Ohm's law. That's the importance. Right? Don't write this as V equals IR. That is not V equals IR, that is delta V equals IR. Upgrade yourself. Upgrade yourself. Right? I mean, without knowing the difference between V and delta V, you will stuck in A-level questions. You will get stuck. Right? Starting from today, now itself, get used to delta V equals IR. Delta V equals IR. Right? So this is how delta V equals IR is applied. And this is how we deal with circuits. These are conducting wires. Right? Batteries. So mainly, you will see batteries and resistors in the first part of electricity here. Right? And there are more electronic appliances and devices coming up in electronics. Right? Especially diodes. LED is also a type of diode, light emitting diodes, and bipolar transistors, unipolar transistors, and op amps. Right? There are specific things also coming up there. Here in electricity, in these parts, mainly we will be dealing with resistors and batteries, and we will be going into like depth, very deep in these things. Right? More things are coming up. Right? So now raise your hand if this is clear enough, and if not, forward all your questions now. You can take this down as well, this example. While taking down, forward all your questions if there's anything more to clarify from my side. Okay, take it down. While taking down the example, while taking this down, while take down the example, if you have anything to clarify further from my side, you can forward them. This is a very interesting lesson, right? Very interesting, right? If someone says current electricity is not interesting, that is totally because of the person you have learned it. I'm honest. Otherwise, this is a very interesting lesson. Very interesting lesson. One of the most interesting lessons we have in our lineup. And one of my favorite lessons. Right? Very interesting. And very practical. But just talk to your friends and check with them. Like a substantial amount of students say that current electricity is difficult and they are not comfortable with it. Right? Mainly because they haven't got the fundamental concepts properly. Right? And to be honest, that responsibility is with the teacher. That's the reality. That's the reality. That's the truth. That's the bitter truth. Right? Electricity set උන්නේ කියලා. ඒ කියන්නේ set උන්නේ කියන්නේ comfortable නැහැ කියලා electricity එක්ක. මම නම් වෙන reason එකක් දකින්නේ නැහැ. That's totally on the teacher, on the lecturer. ඒක මාරම interesting lesson එකක්. You will see many things when we are moving forward. Right? There are many things. many interesting things, interesting and practical. ඔය දෙක set වුණාට පස්සේ ඒක නියම එකක්. You will start loving electricity, right? Once you know these concepts properly, you will start loving electricity as well physics, right? It's really interesting, yes. Obviously. Because I didn't make it boring. Revision class වල එහෙම ළමයි එනවා SI එකේ electricity කරන්නත් බයයි. ඒ කියන්නේ they are scared of electricity, and once you understood these theories properly, right, they love doing electricity, right? When you grab electricity properly, electronics is nothing, right? To be honest, electronics is nothing. Electronics is comparatively easier compared to electricity, but to understand electronics, all electricity is needed. So electricity පුළුවන් වෙනවා කියන්නේ electronics ඊට වඩා ලේසියෙන් කරන්න පුළුවන්. Nothing. Okay, right. Write down below with a red pen. Write down below with a red pen. Write down below with a red pen. Potential at positive terminal of a battery. 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 Potential at positive terminal of a battery is greater than potential at negative terminal of the battery. Is greater than potential at negative terminal of the battery. Is greater than potential at negative terminal of the battery. Is greater than potential at negative terminal of the battery, right? Next point, keep using red. Next point, keep using red. Electric current flows from high potential to low potential. High potential to low potential. High potential to low potential. Within brackets, high voltage to low voltage. Within brackets, high voltage to low voltage. High voltage to low voltage. High voltage to low voltage. In the circuit. High voltage to low voltage in the circuit. High voltage to low voltage in the circuit. Right? One more thing. I'm just sharing this, assuming that you might get confused sometimes if you refer this again. See, I clearly said current flows from high voltage to low voltage in the circuit, right? In the circuit, not in the battery. Battery behaves opposite. That we will see in the coming parts, because battery is the source here. Source එකට එහෙම වෙන්නේ නැහැ. Battery is the source. I clearly said current flows from high voltage to low voltage in the circuit. Source එක ගැන කිව්වේ නෑ තාම. source එක කියන්නේ මෙතන supplier මෙයානේ. supplier තමයි battery එක. battery is the supplier here, source here. source එකේ behavior එක different. behavior of the source is different. That you will see in the coming weeks. Don't worry about that, just be patient. Right? I hope it's clear enough. නැත්තම් මෙතන battery එකේ වාගේයි from B to 8 flows කියලා. That is the source, not the circuit. That's the source. This is called the voltage source. This is called the voltage source. Okay. Right. So we have come to the end of the planned things, and we can keep the next heading written. Keep the next heading written. We'll be starting from this point next week. Right? Equivalent resistance of resistor systems. Equivalent resistance of resistor systems. Next heading, equivalent resistance of resistor systems. Next heading, keep this written. Equivalent resistance of resistor systems. Listen now, listen. Equivalent resistance of resistor systems. Listen. Okay, so with this discussion, we covered all the fundamental concepts here. Fundamental concepts of current electricity. Right? Even if your electricity knowledge was zero, right? I strongly believe that this simple explanation was enough for you to understand this from zero. There's nothing more to understand here. Right? This is totally it about fundamentals. Right? And everything we are starting from next week will be building up on these things you learned, on these fundamental concepts you learned. Right? Everything will be building up. Equivalent resistance, equivalent resistivity, equivalent electromotive force, potential writing along circuits, right? Many things, most of the things, many things. Potential writing along circuits, then heat dissipation along a circuit, right? Kirchhoff's laws. There are many more things coming up, many more things coming up, right? 18 weeks and 1 day, yes. 18 weeks and 1 day. Right? Many more things coming up based on these fundamentals. Right? So I believe that it was more than clear enough for you to understand from zero. Right? I explained everything from zero. Assuming you don't know anything even from O levels. මම O levels ඒවත් O levels වල කරලා තියෙනවා කියලා කිව්වට even I said you that you have come across this in O levels, but I went down all the way to ground and explained. Right? Even you have done that's 127. It should be less than that. Check the number of days to 10th of August. Should be less than that, right? I guess. I usually don't count days. I count weeks, that you know. So it's 18 weeks. Right? Okay. Then if this part was clear enough, right? If this part was clear enough, I know now it's clear. If possible, you can add a comment to YouTube video once it is ended. Right? Don't add to the live chat. Don't add to the live chat because it will disappear when the video is posted. So what you can do is when the live chat, when the live stream is ended, you can add a comment there as a feedback. Can be negative or positive if you understand it properly, right? Sometimes you might be watching this on YouTube and you might be a revision student, or you might be a first try. First try means you might be a student who are sitting for the exam in 26, right? Or else you can be a student sitting in 27, right? I don't think 28 ones are here, right? Then if possible, what you can do is you can add a comment there, right? Add a comment there to the YouTube video, then everyone else can see how it was, right? How it was, right? Then listen. In our theory classes, now field lessons are ongoing, right? Regular theory class, field lessons are ongoing, and Yeah, you are correct. It's 127. I just checked. Right? 18 weeks and 1 day. 18 weeks and 1 day. Right. So I actually usually don't count days because I prefer weeks. And you also have schedules as weekly schedules, no? And that's how it should be, right? As an A-level student. So in my theory classes, I have told you these things. You have to have weekly schedules, not daily schedules, right? Not weekly. It should be, sorry, not daily, not daily. It should be weekly, right? So even when you are starting the classes, also during the first month, starting from the first month, actually, starting from the first month, I have shared these things with you about weekly plans, weekly schedules, and those things, right? So I know personally, and some students whom I know closely, they have their weekly schedules and they are working strictly according to their weekly schedules and working for like 12 hours to 14 hours these days, right? There are students, right? Even if you believe or not, there are students who work for like 12 hours, 15 hours a day now, right? Always the amount of effort you put into this will return the result to you, right? So whatever you put in as effort, right, will be equivalent to your harvest, right? Will be equivalent to your harvest. That is how it is, right? That's a natural concept, right? Right? If you cultivate good, you will return good. If you cultivate bad, you will return bad. Simple as that. If you put more effort, right, you will get the same in return. If you put less effort, if you uh, like if you don't care these things, right, then exam will also, right, will not care you, will also not care you back. That's the thing. It won't care you. It won't care you, right? Then you will get a tragic F or something, right? That's how it is. That's natural. That's natural. That's natural, right? So just 18 weeks. Listen, and most importantly, New Year is coming up, right? A little bit of a distraction for your momentum, right? Most of you are celebrating Single and Hindu New Year, no? Right? Most of you are celebrating Single and Hindu New Year, no? Single and Tamil New Year, Single and Hindu New Year, right? A little bit of a distraction, but this time, my advice is to just spend your like 14th. I think Nakat things are only on 14th, right? Then just spend your 14 on those things and get back to your track, right? You can celebrate New Year's to the fullest next year onwards, right? That's how it is. And the season coming up is not so good because New Year, Vesak, Poson, kind of a distracting season. But don't let yourself to be distracted by those things, right? Have to bear up, right? That's a sacrifice. Above all, that's a sacrifice. That's a sacrifice that you are going to do during these 18 weeks, right? And that's going to pay you back in your entire lifetime, right? It will pay you back in your entire lifetime, maybe for 40 years, 50 years of time here onwards, right? It will pay you back, right? Then sacrifice these 18 weeks thinking about a fruitful 40 years or 50 years of time, a whole lifetime, simply whole lifetime, right? That's how it is. Okay, then. Okay, then anything else to know? Anything else to know? Anything else to know? And I discussed with the institute for the optics seminar, and institute will be closed 12th of month 12th තියෙනවා කියලා paper class එකේදී කිව්වනේ 12th month. I mean tentative, as a tentative date I told you I'm checking the availability on 12th April කියලා කිව්වනේ. And they said they will be closed on 12th. If the institute is closed, I can't have the seminar there because it's going to be a night seminar. Then I can't control all of you who are there physically, right, in a night seminar. during breaks. Usually you will get 2-3 breaks because that is going to be a long seminar, right? Minimum you will get 2 breaks, right? So therefore, since the institute is closed, most probably I will talk to them again tomorrow and confirm you through the channels and groups, right? If 12 was a holiday, I mean, if not a holiday, sorry, if 12 was a closed day of the institute, I'll be shifting it to 19th or 26th, the other 2 Sundays, right? One of the other 2 Sundays in April, right? 19th or 26th. That we'll see. I will update you accordingly, right? Okay. Right. Okay then. If no any other questions, we can wind up. It's 2021. Okay. We'll wind up. Any other questions? Please, this time 12 MCQs came from. What do you mean this time? Sir, can I explain about the weekly schedule? I explained in the class already. Remind me in the theory class. I'll remind you again. I have explained already. Remind me in the theory class again. Right? Remind me in the theory class again. Right, okay. Then no questions. We can wind up and make sure you are writing papers in weekly basis. Right? Make sure you are writing papers in weekly basis. And you are getting the ranks. Right? And I have noticed there are some students who are not submitting the paper for grading, but you are in the discussion, right? Without receiving the rank, right? Without being absent, that's also good. But when you have the option to submit the paper and get the graded paper with the rank, right? That's the indication that you can get about your level, current level where you are, right? So do it weekly. And almost all of the physical students are writing papers in weekly basis, and I noticed this especially in online students, right? I noticed this in online students for 3-4 weeks now. There's a drop of number of submissions from online ones, but you are in the discussion, right? It is better you are being in the discussion with the paper, but try to means you have to write to get the understanding about the level, right? And to improve, because to improve, first of all, you have to know your level, right? So if you got a rank in first 5 only, I will say it out in the class, right? Otherwise, your rank is visible only to you, right? And only to me, right? Okay then. Then yeah, keep that in mind, especially for the online students. Physical ones are writing, that I have seen, especially for online ones, right? Have a fixed time. Have a fixed time in the week. In the sense from Tuesday to Friday, to write your paper and submit it. Do it as a weekly thing. Right? That is for 26 paper class students. So in paper 12, 13th MCQ came to our term test. Really happy after seeing it in term test. Paper 12, 13. I can't remember the question now. Can you give me 1 minute? I can check it out. Paper 12, 13. Paper 12, 13. Paper 12, eh? Paper 12, 13. Paper 12, 13. Hydrostatics. Is it? Law of flotation? Yeah. Right. Is the numbers are also same or the same question with different numbers? To find answer, right? Numbers are also same or same question with different numbers. Numbers are same, right? So probably source might be same because I'm also referring some sources when finding questions for you, right? Right. So sources in the sense books, some papers, provincial papers, terms papers, and a book, objective physics, right? There are some more books, right? Sources would appear, some online sources, right? Then I can't remember the source now. Source might be same. Possible. Source might be same. Okay. Sure. All right. All right then. And listen, since I saw that in the chat, this is the same thing. I mean, that is the exact same thing you are going to see in the main exam also, right? Questions will be same as what we are doing in the paper class, right? For sure, that's how it is, right? You will get same questions, same concepts. We have same concepts. You will see the same questions, similar types of questions, right? Especially you can notice the patterns when we were doing past papers in S2 discussions also, right? So in like consecutive years or maybe close years, how many repetitions there were, right? S2 වල දැකලා තියෙනවනේ. එහෙම තමයි main exam එකෙත් වෙන්නේ. That's how it is. That's the importance of practicing papers. Then you know all patterns, right? Then when you feel happy that much when you see same type of or similar type of a question in the term test, right? Just imagine how would it be when you see the similar type of a question in the main exam, right? To feel that real happiness, now we have to practice more, right? Don't miss papers, right? නිකමන නිකන් බලන්න now we are writing, we have finished 12 papers, 12 full papers in the paper class now. 12 into 50, right? This much of MCQs you have practiced now. 12 into 50, 12 into 50, right? 600, right? Right? Like 600 MCQs are practiced so far, which means 600 types. That's the thing, right? 600 types. 600 types. Now, by the end of paper class, right? You can check the count. Now, if you add this, add past papers to the same count, then you will see a count around 2,500, 3,000, something like that, right? So, practicing that much of questions, we are going to sit for the exam to write 50 MCQs, right? So, don't worry, this is very much doable when you have the correct guidance. The thing is, now when I deliver these things from my side, you have to admit them from your side, and you also have to work accordingly, right? Otherwise, like in last time also, we have several examples from the results came in last time, right? The only thing that I can do is guiding you to that goal because I know how I should guide you, right? Then admitting the advisors and working accordingly is it's totally up to you, right? Then if you work that way, right, definitely you will ending up having the anticipated thing. That's how it is. That's how it is. Otherwise, I can't sit for the exam and right now. That's the thing, right? I can guide you, right? Closely and carefully, I can guide you. And admitting those things and following my guidelines and guiding all the things is something on you. That's the thing. So when both of our deliverables met together, then it's going to be right. This is coming from teachers end, right? One thing is coming from teachers end, and in A levels, the majority is coming from students end. This is the reality, right? Guidance is coming from teachers end, and the majority is coming from students end. And when both meets together, right, you are going to get your right anticipated result, anticipated goal, right? That's how it should be. That's how it should be, right? Then so as I deliver my best here, you should deliver your best from your side. Then best to best will meet, and you will ultimately reach your goal. That's how it works, right? Okay then, if no any other questions, we'll wind up. It's 10:30 almost. It's 10:30, right? Okay, then stay safe and keep in touch. Stay safe and keep in touch. Refer these things again before you are joining the next class, right? We will be continuing off from this point onwards next day, right? Okay then. Then work hard. 18 weeks. Keep that in mind. You are starting the 17th week this Monday, right? 17 weeks starting from the Monday, right? Work hard and don't waste your time. Utilize and optimize your time properly. And feel free to call me if anything. Call or text me. Not actually call, because I usually don't pick up calls if I get during a class time. If not, if I was free, I can pick up, right? So if you need to get something clarified like in an urgent manner, usually I reply WhatsApp messages during classes, right? Now also I have got several messages. For some messages I have like replied as I got free times, right? When you are doing calculation, sometimes when I let you do the, like, if I give you some time to do something, right? If I saw a message coming up, I reply for WhatsApp messages. So if anything, feel free to contact. Okay then stay safe, work hard, and see you in the next class, right? Good night and goodbye. See you.